just a reminder here, some of the solubility of ionic compounds. Some ionic compounds are very soluble in water. Some are only slightly soluble. And if you want to determine if a compound is soluble, we use the solubility chart. And remember, we have a pattern for doing that, right? We look for the negative ion across the top of your solubility chart, and then we find the positive ion in one of the two basically rows below it, yes? So we look for the negative one across the top and then the positive one, okay? If it's in the bottom row, right? So our example here, guys, is iron 3 hydroxide. We would find OH minus across the top, right? And then underneath OH minus, we'd have two categories there. And you would have to find where's Fe3 plus in this case. So Fe3 plus, I believe this says most down here. And there's a list of a couple things up there like so. And Fe3 plus would be in the most category. So since it's in the bottom, we would say that that is insoluble, okay? Or we would say slightly soluble, or we would say solid or precipitate are all words that we would use with that. So that's why we put a little S behind there. So we'd have FeOH3 solid, okay? In other words, doesn't break up particularly well in water, okay? If we looked up sodium chloride, of course, okay, NaCl, we look for Cl across the top. And once again, across the top, we'd find Cl. Whereas Na1 plus, it's probably in the top part, right? I believe there's a list of stuff down here, and it's not down there, so it must be up here in the most category, or group 1 maybe it says, I don't recall. Does it say group 1 or most? Yeah? Group 1 or most up here. And in this case here, since Na is up there, Na1 plus, it is very soluble. So we would use the term very soluble, aqueous, soluble in water, and that's why I put a little AQ behind there to represent very soluble. Okay? So just a little reminder about ionic compounds with that. Okay? Once again, you want to break these ionic compounds into the two ions, and you want to test for those, right? So aluminum sulfate. For aluminum sulfate, this is what you're looking for, right? Look for that across the top, and then find Al3 plus. Is it in the top middle part there, or is it in the bottom part? And then go based on that, okay? And once again, here's a few other examples here. This is fairly important, guys, so I would strongly recommend, we did some questions with that the other day, and make sure you have those. We went over those in class last Friday, I believe, before the break there, so make sure, okay? All right. Today, before we go to the lab, we have to understand differences between ionic and molecular compounds. So we need to be able to classify ionic and molecular compounds, acids and bases, on their properties. So solubility, conductivity, pH, and their states, okay? So we've talked about solubility for ionic compounds already. We'll talk about pH and states and things like that. Relate the molecular structure of simple substances to their properties. Describe how the properties of water are due to polar nature of water. And relate this property to the transfer of energy in physical and living systems. So we're going to look at that as well, okay? What are properties of, last day we did properties of ionic compounds, okay? What are the properties of molecular compounds? Well, they're composed of non-metals, right? Non-metals. And they are held together by covalent bonds that are formed when non-metal atoms share electrons. By the way, guys, you should probably know that. Covalent bonds is the sharing of electrons. That's what it means. Covalent bond, sharing of electrons. Make sure you write that down somewhere. Covalent bonds, sharing of electrons. Okay? Now, the covalent bonds within, and this is important, now pay attention here, guys, this is actually Chemistry 20 as well. The covalent bonds that occur within the molecule are pretty strong. Okay? So what holds that molecule together, the sharing of electrons, is fairly strong. The forces that act within the molecule are called intramolecular forces. Intra. Okay? So if you think about, if you're an introvert kind of thing, you're about yourself kind of thing, right? You think about, you know, what holds me together kind of thing. That's intramolecular. Intra. Okay? Now, that's what holds one molecule together. I'll give you an example. What holds many molecules together? Okay? So the attraction between molecules is something called intermolecular forces. And they're usually much weaker. Okay? Intermolecular forces. That's between, you know, if you're between intermolecular forces. And they're quite a bit weaker, those. So that's what holds molecules together. Okay? So the difference is, we'll talk about this in a second, I'll give you some examples. Intra and inter, we need to know the difference. Okay? Make sure you study that. So, this is an example of the two. Okay? Don't even worry about this for right now. In fact, I'm going to cut this off here, like so. All right, oops. Let's go back up here for a second. Right there, okay? So, this is an H here, by the way. Sorry, it got kind of cut off here. Okay? This is a water molecule. That's one molecule of water. You would never see this one molecule of water. It's too tiny, okay? This one molecule, these are called covalent bonds right here. So this is your covalent bond. And so is that there. That's the sharing of electrons between those two. Pay attention. Okay? Sharing. That is called intra. That's what holds one water together. Intra. Okay? Intramolecular force. It's what holds this molecule together. That's intramolecular force, otherwise known as a covalent bond. Intramolecular force, otherwise known as a covalent bond. Okay? That's what makes that one water. Okay? When you drink water, though, you probably don't drink just one of those, because you would never know. Okay? They're so incredibly tiny, you would not be hydrated if you drank one of those. You probably drink lots of them. And when you drink lots of them, they are connected together. Okay? Like so. So, I'm going to split these right here. Okay? Notice, intra, right here, intra, but connected between these two, what connects these two molecules together, what holds them together? And the answer is intermolecular force. Inter. Okay? That's a special one. This one's called, you don't have to know this yet, this is called hydrogen bonding, okay, down the road. But that is what holds one water to another one, to another one, to another one, so that when I, you know, for example, take a drink here, you know water's a liquid, right, at this temperature anyway. What holds all these together? And that is the answer, is what holds all those waters together so you can see them? Intermolecular forces hold them together. Okay? All right? Questions about that, anyone? Inter versus intra. Intra holds one, inter holds many. There's probably in this bottle here, I could actually probably tell you. I could probably weigh it out and figure it out, but I bet you there's probably easily over, I don't know, there's probably like 6.02 times 10 to the 23 waters in here. Lots. 601, or sorry, 602 with about 21 zeros after it. Okay, that's how many water molecules are in here. And they're all linked together through intermolecular forces. Okay? That's the difference between the two. Melting points. In molecular compounds, only a small amount of energy is required to cause the molecules to move apart from one another. So there's only a small amount of energy to break those intermolecular forces. Okay, look here. When I talk about intermolecular forces, I'm talking about, hey, how would I break these two here, right? Between the link between these two. How would I break that link like that? And the answer is, I would heat it up. Okay? What happens when you put water on a stove? And you start to turn it up, yeah? It boils. What do you get when you boil water? You get water, vapor, or steam, or basically the gas version, yes? Okay? So what you're doing is, look, when you guys give these molecules energy, they start to move, right? Think about ice. We go outside, we grab some ice. Is there much movement in ice? It's a solid, right? They're linked together. They're holding each other together, okay? The solid, you can walk on it, for crying out loud, yeah? Right? Most of the time. You can drive trucks on them sometimes. They're locked together so well. When it warms up and it gets above zero, what happens? Those molecules that are sitting there that are locked together, they always have energy. Those molecules have energy. Okay? They're sitting there, they're actually doing this. They're vibrating back and forth. Ice, if you looked at ice, it would be doing this. They're just moving back and forth very slightly. But if you start to heat it up, what happens to the molecules? They start to move faster, right? That's called kinetic energy. We give them energy. So they start to move faster. Now what happens? They start to do this, right? What is this? They're moving back and forth. There's still an attraction between them, but it's not as good anymore. So they start to do this, and now you get, oops, that, right? Now you get water, because it's able to slosh back and forth. Yes? Think of water. You know, what does water look like? It sloshes back and forth, right? That's the molecules moving back and forth like this. And then you put them on the stove, what happens next? Are they still doing this? You're giving them even more energy, right? So now what happens? They start to do that. And now they start going off in their own direction. Now they're a gas, right? This one's not linked to this one anymore. They're independent. Well, they're not independent of one another, but they're free to go. They have enough energy to be on their own. We've completely broken that intermolecular force. Okay? That is melting point, boiling point. That's the different states we have, solid, liquid, gas. And it happens for all of them. Okay? Not only these kinds of compounds, but also ionic ones as well. But to break that intermolecular force doesn't take a lot of energy. Intermolecular forces are weak. Okay? When this occurs, the compound melts. Not a lot of energy is required because the force attraction between molecules is weak. When a molecular compound melts, the molecule itself does not break down. When you take sugar, okay, sugar. If you melt sugar, what do you get? It's not a trick question. You take a cube of sugar, and you put it in a pot. What do you get? Liquid sugar. Okay? It doesn't break down. If you take water, okay, and let's take ice, and you heat it up, what do you get? Liquid water, right? You keep heating it, what do you get? You get gas, right? Liquid or water gas, right? It doesn't break down, guys. It just changes states, basically. They still stay together, okay? They still stay together, all right? A molecule is neutral because it does not have an overall charge. So these are not ionic compounds, right? Sodium loses an electron, chloride gains an electron. 1 plus, 1 minus, give and take, charges. These don't have charges. These are neutral. So because of this, a molecular compound will not conduct electricity as a solid or as a solution. Okay? Crystals of molecular compounds crumble easily because the attraction between molecules is weaker than the attraction between ions in a molecular compound. Okay? Solubility. This is where it gets a little tricky. Some molecular compounds are soluble in water, like sugar, for example, is soluble, and that's mostly because sugar is also polar. We know water's. We went to the lab, remember, and I bent water with the rod. Yes, okay. Water's polar, so is sugar. So sugar dissolves nicely into water because it's polar. Water's polar. Water says, "Hey, I got a negative end." Sugar says, "Hey, I got a positive end," and they attract each other and they pull apart. When we put sugar into water, what does it taste like? Sugar water. Because it pulls the molecules apart, but it's still molecules of sugar. Individual ones, though. Okay? While others, like wax or oil, like if you have cooking oil, you know, like a Pam, you know, or Crisco, or vegetable oil, or whatever you guys use in a pan, that is non-polar. So if you put oil into water, water says, "Hey, I got a negative end and a positive end," and cooking oil says, "I don't have those," so it doesn't break up. Okay? Because it doesn't have that negative or positive end. So some things are soluble, so other things are not. Okay? Now, acids is probably the next big thing we need to talk about. Arrhenius was a guy that did a lot of study on acids. And he basically proposed that acids release hydrogen ions. So this H plus here, this is what is responsible for acids, guys. An H plus, okay, when dissolved in water. So hydrochloric acid would give you this right here, and that is a measure of pH, okay? So when you stick pH paper or pH meter or pH paper, which is basically just different colors, okay, that's what it's measuring. How many H pluses you have in that solution, okay? All right. Properties of acids. Acids are sour tasting. You might say, and we will probably not investigate this in the lab, so please don't drink the hydrochloric acid, okay? We call that natural selection. We don't want to be that person. Don't drink the acids. You might say, "Well, mister, how do you know it tastes sour?" You all know it tastes sour, do you not? You guys ever eat a lemon? Yeah. Vinegar on your French fries with black pepper, so good. Hey? Yeah. Vinegar. Yeah. In fact, little tidbit of information for you. You want to pay attention. This is going to help you out. You ever have the hiccups? You got the hiccups and you can't get rid of them? What do you do if you got the hiccups? What are you supposed to do? How do you get rid of the hiccups? Yeah. Hold your breath. Hold your breath. What else? Hang upside down. Drink water upside down. I've seen that one. What else? Get scared. That never works. What else? I'm just saying, this is what I do. I don't usually get the hiccups. I don't get them a whole lot because I've scared them off with my routine. You ready for this? Darby, you ready? Ooh, no. A tablespoon, so like a soup spoon at home, full of vinegar. Straight, no water, straight, done, guaranteed. Hiccups are over. I'm just saying, that's how it works. Seriously, not lying. That's what I do. Tastes horrible, but it's like Buckley's. You just gotta take it and you just gotta do it, and then it's over, right? It works for me. All right. All right. Acid-base indicators are chemicals that are used to determine the solution is acid or base by changing color. Litmus paper is an example of an acid-base indicator. Okay. Now you need to know this. Litmus paper, an indicator, turns red in the presence of an acid. So usually that means we'll go from blue to red, or litmus paper comes in two colors, blue and red. So if you put blue into an acid, it turns to red. If you put red into acid, the red litmus paper, it turns to red. Okay? So if blue turns to red, or red stays red, it's an acid. Okay? Depending on which one you're using. All right? So, acids have a pH that's less than 7, right? We know that from before, do we not? Yes? Less than 7. Acids react with metals. Acids conduct electricity. Acids feel wet. Okay? In other words, they feel like water. You will not know that you have acid on your hands until you feel the burning. Okay? When you feel the burning, that's when you know that you have acid on your hands. That's pretty much the only way you'll know. So don't dip your fingers in there and be like, oh, I wonder what this is. Because it's going to feel like water at first, followed by burning. Don't do that. Okay? That's a bad decision. Also, natural selection. Don't do that. Okay? And if you have any cuts on your hands, it's going to feel 10 times worse. Guaranteed. Okay? Like I said, it feels like water. You won't know until you feel the burning. When you feel the burning, what do? No. What do? Huh? Put water on it. That's the only thing you can do. Okay? You're going to rinse them off underneath the tap, and you'll hold your hand there for as long as you can. Okay? That's all you can do. If you get it in your eyes, I will shove your head into the eye rinse station. You ever have water in your eyes? You ever have cold water in your eyes? Multiply by that by 10, that's the feeling that you're going to have. So put your goggles on, is the moral of that story. Okay? Because I will shove your head in there. That's your only option. Okay? Sorry. That's it. Ah, your face, your eyes. They'll get a nice bath. Yeah. It's not enjoyable. No, it's not going to be enjoyable. So just put goggles on. It's easier. Okay? And we'll wear aprons and we'll be fine. The acids that we're going to give you are not going to be like, they're not going to eat your face off kind of thing. They're not. It's not dumb. We're not going to be stupid, right? But, you still got to be careful, guys. Okay? You might say, well, that kind of seems silly. Why do we talk about those things? Because, well, there's some There's definitely some different things with bases, okay, that we need to be aware of. So you need to know all this. Very important. Okay, we're going to do that in the lab next day. How do you recognize acids? It says acids tend to contain hydrogen on the left side of the formula. Not always, but mostly. Okay, look at, what do these all have in common? HCl, H2, SO4. That didn't turn out so well. HNO3, H3PO4. This one doesn't, but actually this is the one that could go right there if you wanted to. In fact, we could rewrite that differently. We could call it HCH3COO, okay? Which would be vinegar, acetic acid. Okay, it says ethanoic acid, but that's another term for that is acetic acid. Ethanoic acid is the fancy term for it in vinegar. Okay. By the way, if you're going to actually drink the vinegar thing, like I told you, make sure you get the store stuff. Don't get the stuff from the lab. The lab stuff is like 1,500 times more concentrated. It's not good for you. Okay, that won't be good for your tummy. Okay. And don't worry about that one either there. So notice all the H's kind of at the front. That's how you're going to know. Bases. According to Arrhenius' theory, he said anything that contains hydroxide. So we're looking for this OH here. So when you put sodium hydroxide into water, you get sodium ions and hydroxide ions. And his theory is anything with hydroxide is a base. Okay? And in fact, you might want to drop the base. Boom, 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 boom. Yo, yo, yeah, you can. All right. Boom, boom, boom. That's funny stuff, laugh. Okay. So hydroxide is what you're interested in there. Properties of bases. Bases are bitter. Who's drank bases before? Probably not much. And they feel slippery. We will also not test this in lab. This is the difference between an acid and a base right here. They feel slippery. Okay? Bases are bitter. Most of us probably haven't tasted a base before. Bases would be an example of like Tums would be a base, but Tums have like flavoring in them, right? Like they taste like fruit. You know, ooh, this is good, but it's not. That's not really a base. That's the artificial stuff. Bases are bitter. Okay, we're not going to taste them. Bases are actually more dangerous than acids to you, so you do not want to mess with bases either. Okay, in case you're thinking. That's why if we had acid on our hands, we wouldn't put base on it because that would just, that's a potential nightmare there. We have acid and base, and they're both bad for us. Okay, so we're not going to test that in the lab. You will know if you get a base on your fingers, though. Okay, that you will know right away because usually they are very, very slippery. So it's like having like oil on your fingers, like from a car engine or something. It's super slippery. Okay, super slippery, and usually the slippery thing comes right before the burning thing, kind of thing. So you'll be like, hey, my hands are really slippery. And then you'll be like, my hands are really in a lot of pain right now because it'll feel just like an acid, guys, except you'll get that little bit of notice before because they're very slippery. So it's slippery, and then you'll be like, ah, burning. That's what's going to happen next, okay? Bases turn litmus paper blue. So either red to blue or, of course, blue would stay blue. Okay? Because remember, there's two pieces of litmus paper, red and blue. Okay? So either blue will stay blue or red will turn to blue. And I got an acronym for you. I don't know, maybe it's not a synonym. I don't know. Some English term, right? I have no brighter, clever friends or something like that. By the way, they will conduct electricity, and they do not react with metals. So those are some differences there as well. This is how I remember it. Bases turn red litmus blue, or BRB. Be right back. Remember? BRB. Bases turn red litmus blue, and acids do the opposite. So acids have to turn blue litmus red. Okay? That's how I remember it. So bases, red, blue, red to blue. Acids turn blue to red. Okay? So that's kind of, like I said, how I remember those. So BRB, be right back. If you want to recognize a base by its formula, most of them have hydroxide, OH minus. So this is what you're looking for. When I look at sodium, look right here, sodium hydroxide base. Yes? There are other kinds. This is probably the only other one that we really need to be concerned about, and that is ammonia. Not ammonium, ammonia. Ammonia is what they use in Windex. You know when you spray Windex and you know that smell that you get? That's that clean smell or whatever. You know, I don't know what we want to call it. But it kind of catches you in the nose and it's like, that's ammonia. Okay? Comes in Clorox as well, bleach kind of thing. But that strong smell like that, that's the ammonia. Okay? If you have skunks underneath your front step, you could spray ammonia in there and then run. Okay? That's what I did. There was none underneath there at the time. I kind of knew that, but I wasn't 100% sure. Little tip for you. Yeah. Yeah. Okay? Last, real quick here, some properties of water. Okay? Water is polar. We already know that. It's got a partially positive end and a partially negative end. So if you look at this diagram here, guys, this would be the H, this would be the O, and this would be the H here. That's what water looks like. Okay? That little funny symbol there that you see kind of looks like I just do a music note, by the way. I just kind of do that. Partial positive means it's got a little bit of a positive end, and oh, sorry, wrong way. A little bit of a negative end, and a little bit of a positive end here. Okay. And because of that, because water is polar, it leads to a lot of the properties that we already know about water. Okay. Like when we went to the lab the other day, and I had that, I charged up the golf tube there with the bunny, and I held it near the water. That's why it curves, because the negative ends are attracted to the positive ends of the golf tube, and that's why it curls like that. Okay, so it's got a partial positive and partial negative. Water molecules are attracted to one another. That's why do you find water as a liquid at room temperature? Because they're linked together. Inter, right here, guys, intermolecular bonding, okay, also known as hydrogen bonding in this case, okay. Hydrogen bonding explains special properties of water, including its relatively high boiling point. Because of hydrogen bonding, water boils at 100 degrees Celsius. If you know what, if we didn't have hydrogen bonding, that special intermolecular force, water would boil at negative 100. Okay? That's the trend that it would follow. It basically boils. That's 200 degrees difference. Negative 100 to 0, 0 to 100. Thank God for hydrogen bonding. Because if water boiled at negative 100, what would that mean for us? Yeah. All the world's water would be a gas. We could breathe water. We'd be fish. Okay? You wouldn't be drinking water, though. Right? We'd have no lakes. We'd have no rivers. Be all gas. So hydrogen bonding has that. It has a high surface tension. You know how you sometimes put something on top of water and it just floats there? Right? Or the little bugs that kind of go along, right? Why do they do that? Because water, that intermolecular bonding is very strong, and it's that surface tension. When you fill up a cylinder sometimes and you overfill it, you get that little bubble at the top, don't you? Right? And it doesn't quite spill over. You get a skinny enough glass, you'll see that bubble. It sits at the top, you can fill it up like that, right? That's hydrogen bonding. That's the intermolecular forces holding the little waters together, making that little dome there for you. Okay, and the ability to of ice to float. That's why ice can float as well. Okay, what do you think will happen? We already did this. Water is amazing. All it is different ways that they've arranged themselves together. Okay, so the water's different ways that they arrange them. Ice kind of takes on this shape here. Water, the ones that we drink, kind of have some that are connected, not all of them. Okay. And steam, of course, they're all independent of one another. Okay? You know, that's why we're able to skate on water, because it's joined together. They're all held together, right? Okay? It can defy gravity. I think we might have talked about this. How does water get up to the plant, or how does water get up to the top of the tree? Polar, right? This water is connected to this one, which connects to this one, and they kind of help each other pull them. Guys, you're going against gravity. Should be going down, but we suck up water from the roots, and it's polar. It's cohesion, adhesion, side of the walls. It goes up through the xylem. Yes? Is that a term we know? Yeah. And gets distributed to the leaves, and that's where photosynthesis takes place. Right? And carbon dioxide, all that stuff. Yes, we'll talk about that down the road. Water keeps up your energy, weight down, muscle strong, joint supple, digestive system smooth, your whole system in physical balance. It regulates body temperature, makes up to 83% of blood, removes waste, composes 75% of the brain, helps carry nutrients and oxygens to cells, moistens oxygen for breathing, helps convert food into energy, protects and cushions vital organs, helps body absorb nutrients, accounts for 22% of bones, cushions joints, makes up 75% of muscles. Okay, and this should be in there as well. You can read through that as well. Okay, so it's pretty important right, for us. Yeah, okay. All right, so you guys have some questions to do there. You should go back through the notes and fill in the, we're going to skip this here, but go back and make sure you fill in the notes from the Google Classroom there. So you got some stuff to fill in, and you have some homework questions there to do as well, so make sure that's done for tomorrow. There should be a pre-lab thing there for you to do, I believe, as well, if I'm not mistaken. If not, well, that's fine. Just do whatever's on Google Classroom there, and tomorrow we'll go to the lab.